Say good morning, good afternoon, good middle of the night, whatever the altitude of the sun is where you are in the world, you are very much welcome here, and we're very glad to have you joining us today. My name is Lauren Harrington, and I will be your host for the duration of today's How-To Hour. Now, we have got a great speaker lined up for you guys today, but before we kick things off with the main presentation, I have a few quick announcements to make. First of all, our special announcement. This year, the AAVSO is both honored and thrilled to be celebrating its 110th year of citizen science and continuous stellar data. We want to give a huge, heartfelt thank you to everyone who has contributed to this accomplishment. We are especially excited this year to be celebrating our 110th anniversary at our in-person spectroscopy workshop and in-person annual meeting. These will be held on November 3rd through 7th in Somerville, Massachusetts. Our annual meeting is also going to have an online viewing option for many of its presentations, so that those of you who can't attend in person can still enjoy the show. We are currently accepting abstracts from attendees who wish to give an oral or poster presentation on their research. So if you are at all interested in any of that, please visit that link right there on the screen. That's aavso.org/110-annual-meeting. And there you will find more information on the spectroscopy workshop, the annual meeting, abstract submission process, and the registration links. Now, let's go through the rest of the announcements. First of all, today's webinar is a how-to hour, which means that we are going to focus on interactivity. At the end of the presentation, we're going to try to address all of the questions from the audience. So if you have any questions about visual observing that you have just always wanted to ask a true expert, today is your lucky day. If you're watching this on Zoom, then all you need to do to submit a question is to click on the Q&A icon down at the bottom of your screen. Type in your question and hit submit. On the other hand, if you're watching this on Facebook Live, you can post your questions in the comments section. Remember, you can submit as many questions as you want at any point during the how-to hour, including during the presentation. So don't worry, it's not going to interrupt the speaker when you do. Next, if at some point during the webinar you experience technical difficulties with audio, we are unfortunately not able to help from here. However, you can probably fix the audio yourself. All you need to do is click on that little up arrow button that's down by the mute icon at the bottom of your screen, and then tinker with your audio settings. Also, automatic closed captioning is now available, which reminds me that I don't think I've started it. So live transcript, enable. Okay, it's now available. To enable or disable these automatic captions, just click on that little CC button, which should have appeared down at the bottom of your screen, and use the menu that pops up. Finally, we would like to thank and acknowledge our sponsors, DC3 Dreams and Voice Astro. DC3 Dreams provides high-end observatory automation and web-based multi-user remote imaging. The AAVSO Net Observatories use DC3 Dreams ACP Expert for the Bright Star monitors and other programs. The AAVSO Photometric All Sky Survey project, also known as APAS, has used ACP Expert's AI scheduler to automatically acquire over 500,000 star fields, hands-off, at a rate of 1,000 square degrees per night. This has resulted in photometry for over 128 million objects in about 99% of the sky. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please do check out their webpage to learn more about their work. Okay, so our instructor for today is an officer of the British Astronomical Association's Variable Star section. And as of today, he has logged over 200,000 visual estimates of variable stars, which is just incredible, and marks him indisputably as one of the most prolific visual observers to ever live. That tremendous experience alone makes us very fortunate to have him here to present this how-to hour. But the act of visual observing itself is not the only relevant task that he has great experience in. He's also drafted hundreds of charts and helped with the redefinition and standardization of comparison star sequences to use modern accurate V-filter photometry. So that helps every estimate from now on. Today, he will be giving us a look into the world of an advanced visual observer, sharing with us some of the history of this artful science, and discussing the ways in which you can optimize your own visual observations. So, without any further ado, please allow me to introduce your instructor, Mr. John Toone.
Thank you, Lauren, for that very gracious introduction. So what I'm going to do now is pull up the presentation, and hopefully you can see. Let's go back to slide 1. Then we're ready to go. Here we go, and I'll go full screen. Can you see the presentation?
Yep, it looks great. Okay,
so we'll start with an introduction to visual photometry. And here is a outline timescale for the evolution of visual photometry, which really began almost 2,000 years ago with the work of Ptolemy. Who produced not only did he do constellation work, but he also produced a catalogue of stars, and he assigned magnitudes to them on a scale of 1 to 6, from brightest to faintest. And then moving on almost 1,500 years, we have for the first time a variable star being measured against non-variable stars. That was undertaken by Tycho Brahe in 1572, when a supernova occurred in the constellation of Cassiopeia. And his descriptions of the brightness of the object against other non-variable stars allowed us to reconstruct the light curve of that particular supernova. Moving now to 1781, science started to appear with the work of Goodricke, who established the eclipsing nature of Algol simply through a visual photometry. Moving further on, William Herschel developed a method of estimating brightness through sequences, which eventually is led to us how we undertake visual photometry today. In 1833, his son, John Herschel, made an appeal to amateurs to undertake visual photometry. And then in the 19th century, mid-19th century, Argelander did a lot of work on variable stars and introduced the step measurement process for measuring the brightness of stars and allocating grades. A few years later, Pogson fixed the magnitude scale on a scale of 2.5 per magnitude. And then in 1863, we have Knott and Baxendale putting together the first observing manual for visual photometry. And in 1882, Pickering made a further appeal, similar to appeal to what Herschel had done, for amateurs to undertake visual photometry. And as a result of that, amateur variable star associations were formed, including the AAVSO, and that is the reason why we're here. Variable star associations were formed because professional astronomers wanted amateur astronomers to undertake visual photometry. So just to advise, visual is alongside photographic, photoelectric and CCD photometry. It's not the only means of undertaking photometry, but it is the original and the longest running series of photometry of variable stars. The photographic period given here is the plate photometry, which was done by Somberg and Harvard, which is now redundant. The photoelectric work started with Stubbings with his work on Algol in 1908 and is still active today. And CCD, of course, is quite popular now with and since the mid-90s. It's now producing virtually all of the V photometry which we have on variable stars. So just to give you a outline, since 1850, we've got about 20 million visual observations have been made by 10,000 observers throughout the world. There are two means of undertaking the photometry, step and fractional. I'll describe that in a minute. It's measured to 0.1 of a magnitude. The accuracy is typically plus or minus 0.2 of a magnitude, which is similar to photographic. Consolidated data, however, which we group in the databases of the associations, it's in excess of 1 magnitude. So that can be considered a drawback, but there are ways around it, which I will explain. So typically, in the AVSO database, you've got a mix of V and visual photometry, which the V is the green, and here is a light curve of SS Cygni. And you can see that the visual photometry and the V photometry is closely related, although there are some differences. Typically on this this particular variable, the V photometry is brighter at minimum and fainter at maximum. And there's a reason for that, which I'll come to also shortly. Typically on a Mira star, you have a mix of V and visual photometry, but look at this, there are still gaps. And so if you just simply had the V photometry, then you wouldn't have a complete light curve. So that illustrates the importance of continuing with visual photometry. So let's go into the methodology on how to undertake visual photometry. So the technique is quite straightforward. You identify the variable and the comparison stars that constitute the sequence. You judge where the variable appears within that sequence, and you estimate the variable brightness between two comparison stars, one brighter and one fainter. You can use either the fractional or the step method. The fractional method is where you have the two comparison stars and you judge the position of the variable between it. The step method is for more advanced observers who can judge the magnitude scale and understand the increments in the order of 1/10 of a magnitude, and judge that when there's only one comparison star available. So once you do the observation, you record the estimate in the logbook together with other details, and then submit the observation to the AVSO, and then the science begins. So typically, let's look at a variable star. Here is a photograph of Serpens Caput, which this is the head of the Serpens Caput, and here is a variable star. Here is Serpens, and we'll just make an estimate with against a chart. Now, apologies, this is a BAA chart, and so we have a lettered sequence as opposed to a numeric sequence, but the principle is just the same, and it's a straightforward process of comparing with comparison stars. So to keep this efficient, what I'm going to say is that we'll use two comparison stars. We'll use E and G at 6.3 and 7.3. So that's a magnitude apart, and use them to compare with OR. So we'll go back to the image. So here is the variable. Here is G, or the 7.3 comparison star, and here is the brighter comparison star, which is 6.3. So you compare where the variable appears between the two. Now, then I would say it's roughly equidistant between the two, in which case your estimate would be halfway point between 6.3 and 7.3, which would be 6.8. If you were to estimate this to be 1/3 brighter than the 7.3 and 2/3 fainter than the 6.3, then it would be magnitude 7. So it's as simple as that. So this is how you undertake the photometry directly using vision. So once you've done that, you just simply log the data. This is an extract from my logbook from a couple of weeks back, back at the end of July. And so you have date, time, you have the star, you have the light estimate, you have the magnitude, the reduced magnitude. You can see which ones are telescopic ones. This is a Celestron 8 telescope. And then there's room for notes if you need to put notes. So that is your logbook. You then put it into electronic form and submit to the Aavso database. So that's how we do the photometry. Now, let's try to make sure that this is as accurate as it possibly can be. Now, note the scattering consolidated light curves using many observers' data frequently exceeds 1 magnitude, is often greater for red stars. And the scatter, the reason for that is you've got multiple observers having different visual color responses, using different techniques from different locations in the world, using different sequences and instruments. So typically here is a red variable star, and typically you've got half a magnitude scatter. The scatter seems to increase as it gets fainter, can be up to a magnitude when you get to this position here. It doesn't look as though, it kind of gives the impression that visual photometry is only in a very approximate science, although you can clearly see what the variation is. So here is a summary of the key areas which will cause scatter in visual photometry. So it's the sequence. The sequence determines the minimum accuracy of any observation. The position angle, personal equation, color response, lack of dark adaptation, and then there's minor items such as is the observer tired? Have you remembered your last observation and it's sort of unconsciously influencing you to think it's going to be something similar? And you have to also think about comparison stars and the variable being close, differing heights from the horizon. So here's a good example of a poor sequence. And a poor sequence afflicts V photometry just as much as it does visual photometry. Take a look at the scatter at minimum with the V photometry. It's over a magnitude. V photometry should never be that sort of range of error. And this is purely down to the sequence being used. And that has to be addressed as the first point to ensure you have good photometry. So there are sequence guidelines. They've been standardized across the world now. I was involved in that work in the early part of this century, and it's roughly listed as follows. So we're using now accurate measurements on the Johnson V magnitude scale. The comparison stars must cover the full range of the variable. Roughly half a magnitude intervals, if that can be arranged. And you don't always have the comparison stars to do that, but this is the guideline, and this is what we try to do. You need a limited color range in the variable because the color response between visual and V is not the same. And so you need to limit that within the sequence if that's feasible. No double stars, and you want those comparison stars in relative close proximity to the variable. So if possible, they can be directly compared. East-west direction is important for position angle, and if possible, the same color as the variable. So the sequence guidelines are being rolled out between the three chart making groups within the world: AAVSO, RASNZ, and BAA. And I was responsible for rolling out these sequence guidelines in each of those countries' meetings in the early 2000s. So this is now the position angle is the next most important point for getting accurate visual photometry. So the upper part of the eye is more sensitive to light than the lower part. And that's because the upper part of the eye is looking downwards and the lower part is looking upwards. When you're looking downwards, you're looking at the ground. You're looking at something which is darker than what you would be looking at something up in the sky. That's for terrestrial viewing. So over the years, the evolution of the human eye has developed to become different sensitivity on the upper part to the lower part. Now, what that means is that when you're looking at a variable star or stars within the field of a telescope or binoculars, the lower star in the field or towards the observer's nose will appear brighter. And the way to deal with this is to use comparison stars in east-west direction so that the level and the position angle is taken out, or orientate the head so that the variable and comparison stars are level with both eyes. Sometimes that's a little bit uncomfortable for observers, but it usually eliminates the issue of position angle. Alternatively, if that's not possible because of the angle of the comparison stars, you bring the variable and then the comparison stars alternately to the center of the field. You take your estimate from that position. So this is a very good example of one of the AVSO observers, a very good observer, Richard Glassner. He wrote to me a few years ago and he asked this question. He said, why do British observers record AT DRAC systematically fainter than everybody else? He thought that we had different eyes or had a problem. The answer is that all the on the BAA chart, all the comparison stars all lay to the south of the variable, whereas on the AVSO chart, all the comparison stars lay to the north. So it was a position angle effect, and that position angle effect can be as much as half a magnitude. So color perception is also important, and this is because the eye is more sensitive to longer wavelength light as the sources increase intensity. So, and there are different effects to different observers because of their color responses. So the remedy here is use the smallest practical aperture available to render the variable and the comparison stars clearly visible in order to dim any color effect. And don't observe the red stars, if they are red stars, in bright moonlight or twilight, because the color contrast will also enhance the issue here. And don't stare directly at a red star if it's distinctly red. Make a quick glance estimate. And so the impact of dark adaptation is also important. If you go out and observe and start making estimates before your eyes are fully dark adapted, then you'll get a different estimate on a red star than what you would do later on once you are dark adapted. And that dark adaptation has a much greater effect on red stars, as per this diagram here. So if you've got a typically red variable, and you have, which is typically B minus V of 1.5. So if you have the normal eye, then it's close to V, and then if it's dark adapted, then you could have a difference of half magnitude. So it does make a difference. So you do need, it's very important to be dark adapted. So summary. To maximize accuracy of visual photometry, use charts with sequences issued since 2002, because they are the ones which are standardized following the international accepted guidelines. Ensure your eyes are dark adapted. Use binoculars or smallest practical instrument possible to render the comparison stars and the variable visible. orientate the comparison stars level with both eyes. This is the position angle effect. And for red stars, apply the quick glance method and try to avoid observing in twilight or moonlight. So following that, if you follow all these guidelines, you can get very accurate results, surprisingly accurate results. If you go back over 100 years, Alexander Roberts did a lot of experiments with visual photometry, and he worked out that he could get an accuracy of 0.04 of a magnitude. And then later on, Frank Bason did some analysis of Albert Jones's observations, and that indicated that he could get to around about 0.05, very similar figure. So this is very good accuracy, which you can do real science with. So so the main point here is that if you adopt the best practice techniques, which I've just described, you can get an accuracy in the order of 0.05 to up to roughly, depending upon the conditions and the sequence and the circumstances of the observation, up to about 0.15, which is still very good and accurate comparable to what you could get with photographic plate measurements. I would say that an individual visual observer's data can be equal in accuracy to some combined CCD observer data. And I'll demonstrate that in the light curve in a minute. So where there is a lack of V data and any scientist or analysis is looking for minor variations in the variable, it's worthwhile filtering the light curve to show a single visual observer's data. And again, I'm just going to show that with a few light curves. So here's a light curve of a Myra type variable by a single visual observer, a very good visual observer, Charles Butterworth, the first observer to accrue 100,000 observations back in 1939. This is his light curve of Ursa Majoris, and you can see very clearly the difference in shape of the light curve from each cycle, and the subtle differences coming out here. And this is picked up, and often this is missed in combining all the observers' data. You just see a mass of data at this point, but just doing one observer's data, you can get quite a bit of information. And this is Charles Butterworth's light curve of one particular variable star over 100 years ago. And it was showing quite a large range, almost Myra type. But then you compare it with some of my observations not too long ago, you see that the form of variation has changed in 100 years, but it's actually starting to come back again. And so this is the value of long-term visual monitoring and looking at individual observers' data. So this is VBOO, which is the same star you've just been looking at. And as you can see, in recent years, the range is increasing. So it's going back to the mode of variation, which it was undertaking at more than 100 years ago. And this shows a single observer, my observations of or Corona Borealis just prior to its fade back in 2007, shows that the pulsation period was increasing just prior to it undertaking the deep fade. This variation, pulsation variation, was only 0.2 of a magnitude. So it shows you can pick it up if you have a good sequence and you have a careful observer systematically observing this star. Typically, picking up a single observer's data on another Myra star, what I can point out here is that you've got this secondary mode of variation, which is moving down the ascending branch of the variation, and it disappears on this cycle, and then it picks up on the next one. And this can be picked up just by a single observer, as in this case. And here is another observer, some of my observations, which show this is the brightest Herbig star in the Northern Hemisphere, where it's not doing much variation initially. And then suddenly you have what looks like a bit of an eclipse. It's the leading edge of a dust medium. And you can see that after it, after the what appears to be the eclipse, you've got a different mode of variation, including flickering. This can be picked up by visual observers and has been done in this case. So just to move quickly on to the comparison between V photometry and visual photometry. So here we have the various responses in wavelength. So typically visual will be about 500 angstrom, and V, and there is a difference with V. So this is more like 530, and this difference is important because when you come to compare the data, it has an effect. And this is the relationship between visual and V. There's been studies undertaken by Howarth and Bailey and Stanton quite a few years ago now, but you can see that for red stars, there's a significant difference. Around about B minus V of 1, you've got a difference of about 0.2 of magnitude, and this shows up in the in light curves. So you need to have an understanding of that relationship. And so this is borne out in a light curve. This is a light curve of X off, the one, the light curve I showed you earlier, which showed the great deal of scatter. Well, if you look at a single visual observation, observer's data, this is my data, which is the dark circles, you can see it's a very smooth light curve. And then you can compare it with a very good V observer who's got lots of experience, David Boyd, and he's got B and V data here. Interesting to note, the main point here is that at minimum, the V data is fainter than the visual data. At maximum, it's the reverse. And note here, there's a color difference. It actually gets redder as this variable star reaches maximum than compared to what it is at minimum. And that's simply because it's a double star. And when at minimum, the companion star is the dominant star, and it's less red. So here's the calculation. So it gives you, the variable B minus V at maximum is redder than it is at minimum. The comparison stars being used at maximum are slightly less red, and so the color difference between the variable and the comparison star is half a magnitude plus at maximum, and 0.2 of a magnitude at minimum. And that's why you have the light curve comparison between V and visual, and you see the subtle differences. So when the variable is more red than the comparison stars, visual is fainter than V, and it's reverse the other way around. And here's an example using David Boyd's data compared with my visual data. The visual data is the red below, and this is Z Ursa Majoris coming up from minimum light at magnitude 10 up to maximum light at above magnitude 7. And when at minimum, there's 0.6 of a magnitude difference. Visual is fainter than V. At maximum, they're merged. And this can be shown also on this light curve. V here is at the top end of all the visual observations scattered at the base, and at the top, it's merged. In each case, you can roughly see that within this light curve. Here's another light curve of visual data compared to V. This is a very well covered outburst of UGM, and sorry, I should get rid of this. I should have done this before. Sorry if that's been obscuring your view. And so in this case, it's visual data. It's my visual data compared to V data, and what you get is closely allied data until you get to maximum, and that is simply because the color of the variable when it's in outburst is very blue. And so what you get is you get it systematically brighter visually, the difference being 0.3 of a magnitude than V at maximum. But when it comes down to minimum or rising or fading, it's closely aligned. Here's another light curve of visual and V data. This is T Corona Borealis, which is moving from normal state to super active state. And you've got all the visual data, which is in black. And you've got the V data, which is in green. And it kind of indicates that the only reliable data here is the V data. However, if you just plot the single visual observer's data, this is my data, then you get very similar light curve to what you're getting here in partial form, except that it's more complete. And so if you want a full record, a more complete record, accurate record of the variation which is happening here, which is ellipsoidal variation of the variable star in its quiescent state, and then it goes up into maximum, and then what the difference between V and visual, it reduces from 0.4 of a magnitude to 0.2 of a magnitude because the variable becomes more blue. So just to summarize, the offset between visual and V data is determined by the color difference between the comparison stars and the variable. If the variable is more red than the comparison stars, then it is fainter than V. If the variable is less red than the comparison stars, then it is brighter than V. But the important thing to note is the color, the comparison stars color and the variable color is not always constant. So what this is the how-to part of it, but what I wanted to do also is just introduce you to the most prolific, the most outstanding visual observers that are in the world, both in the past and current. And I've set the bar at 200,000 visual observations. Some of the great legends of the past, such as Tom Craig and Leslie Peltier, never got to this milestone. For many years, for a quarter of a century, the only person who'd done it was Albert Jones. But in the last quarter century, quite a few people have caught up. And there's a cluster of these observers who started work in 1975 in the Northern Hemisphere, possibly because of the Nova Cygni that year, that have reached this milestone now. And the latest person to join this is Peter Williams of Australia, who reached that milestone on the 4th of July this year. He sent me an email. He told me he got to the milestone, so I was quickly able to add him to the list. So what I'm going to do now is just tell you about the top 4 observers who've gone beyond 200,000 observations. They've gone beyond 300,000 observations. So these are the top 4. And so we'll start with Gary Poyner in Birmingham in the UK. As of the end of July, Gary's total was at 324,000 observations. He's the UK and European leading visual observer, specializes in CV research, and with him living in the center of a city, he counters the light pollution by using a very large instrument, which you can see there. Typically, this is Gary's work. This is his favorite star, DY Per. And you can see you don't need any other data. You can hear you've got a complete record of the photometric behavior of this star simply from the work that Gary's undertaken. And just to illustrate, Gary's observations are in blue, and this is the full light curve, V and visual, from the AVSO database. And without Gary's input, there'll be quite a few gaps in this light curve. Another light curve from Gary is ORS off, and you can see here 2 outbursts. And one thing to note is that after each outburst, it goes very faint in both cases, and Gary's picked that up. There'll be another light curve similar to this coming. In third place, we have Rod Stubbings from Victoria in Australia. And Rod emailed me not long ago, I think it was the 28th of June this year. He told me that he'd reached his milestone of 350,000 observations, visual observations of variable stars. And so he's hit that milestone very recently. And he is currently the most productive visual observer, making in excess of 12,000 observations per annum. And with the telescope you see here, imaged here, he can undertake visual photometry to 17th magnitude and slightly below. And like Gary before him, he concentrates on monitoring CVs. So whilst Gary's sweeping up all the Northern Hemisphere CVs, Rod's doing just the same in the Southern Hemisphere. Here's a typical light curve from Rod of the brightest Southern Hemisphere dwarf novae. And you can see he's a very busy guy. And this is another light curve from Rod of GW Lib, an outburst. And you can see quite a lot of subtle detail in that light curve, just purely using his observations, which was the majority of the greatest source of data for the AVSO light curve, which is in the top right. In second place, we have Hiroaki Narumi from Shikoku in Japan. Hiroaki is not well known, but he is currently the observer with the most observations who is alive and is still active. Hiroaki reached a milestone of 400,000 visual observations at the end of 2018. He uses the instrument shown on this photo here. He carries that instrument to a nearby rice field, and he does his observations there with this instrument and 7x50 binoculars. And he's quite reclusive. I've not been able to contact him. He's not online. He reports his observations to the Variable Star Observers League of Japan on paper. And so there's always a delay in getting his data into the database. But he's been going since 1975, and he is not letting up. He's within sight of the next person, which I will introduce shortly. Excuse me. So here's a typical light curve which has been produced by Hiroaki. It shows it shows the advantage of having a long baseline of observing, and this shows the long-term variation in a very red carbon star Myra variable. And it shows there are deep minima in 15-year intervals, and this light curve terminates in the early about 10 years ago. He's still observing it. This is a light curve of Hiroaki's for ORS Alpha Uki, showing the 2 outbursts, similar to what Gary's was showing earlier. Hiroaki was responsible, he was the observer responsible for discovering the outburst here in 2006. He was the first person to pick it up, put out the alert, and that's when a lot of science started with all the world looking at ORS Alpha Uki. So moving on to the all-time leading variable star observer, this is Albert Jones, sadly passed away in 2013. He is the only observer to have exceeded 500,000 observations. He's made an estimated 515,000 observations. We don't know for sure because he never kept count. In an observing career of 69 years, he he discovered 2 comets 50 years apart, which is a record. He's done a lot of work. He's been the leading observer in the Southern Hemisphere. He got involved in, he's discovered quite a few variable stars. He's investigated many others and uncovered the nature of several important variable stars. And a lot of the Southern Hemisphere work can be attributed to Albert Jones. This photo is taken at Government House back in 1987, a couple of months after he co-discovered supernova 1987A in the LMC. He's just been awarded his OBE for services to astronomy, ostensibly visual photometry. So typically, this is some of the work that Albert's done. He's been observing for so long that the stars, this star, or Doradus, has changed form in variation, rather like V Bootis was illustrated earlier on. But Albert's own observations can depict that. And here is another light curve of one of his favorite stars, which is AR-PAV, a symbiotic binary, which has eclipses. And when back in 2011, when Albert had to retire from observing, he asked Rod Stubbings to pick up this star. And since then, Rod's been continuing this work. And so this shows collaboration between visual observers. So concluding remarks, visual photometry. It's inexpensive. You can do naked eye work, you can do it with paired binoculars, you can do it with a small telescope. It's easy to learn. Hopefully I've demonstrated that. I would advise that we've now got accurate V sequences tailored for visual observers. They're now available. They weren't available up until the turn of the century. So that makes the science good, and it means the sequences look right for the visual observer. Doing visual observing, you can set up real quick, but be careful about dark adaptation. You can move from object to object very quickly. I can make a binocular observation every minute, a telescopic observation every 2 minutes. And maximum photometric opportunities, it depends where you are in the world, but you don't always have fully clear skies. They're partly clear. You can take advantage of that. You can move across the sky, looking through cloud gaps. And wherever there's a cloud gap, there's a variable star, which you can look at. Visual photometry is instant reduction. So you can put out timely alerts on unusual activity. I'll never forget in 2015, looking at AGPEG and seeing it in outburst. I knew instantly there and then that it had changed mode from declining nova to Z-an star, and that's even before I put out the alert. And so this is another aspect of visual photometry, part of the fun. You see science with your own eyeballs, and by doing visual photometry, you're extending a data series which goes back to, can go back over 200 years, but the bulk of the data has been produced in the past 170 years. Concluding remarks, part 2, understanding the reasons for scatter and optimizing visual photometry improves its scientific value. I've tried to give you a lead on that. I think it's important that overlap between visual and V photometry. V photometry could be the future. visual photometry. I'm not sure how long it will go. Let's hope it will keep going beyond my lifetime. But we need to continue this overlap phase as long as possible, because V photometry didn't come along until so almost 200 years after visual. So we need to keep that overlap going as long as possible, so we can make direct comparison between the two sets of data going forwards. Finally, CCD observers, they've not made visual observers redundant. Lots of people have been saying this over many years now, since the turn of the century. CCD coverage and is patchy for some variables. Same with the photometric studies, which all the surveys which are being introduced now. They're only around so long as the funding is available. Whereas visual photometry conducted by amateurs is not dependent upon funding. It's as long we can do that as long as we want to. So visual photometry can be applied on any variable star which has got a range of 1 magnitude. You can go less if you want to, if you want to challenge, but it's certainly 1 magnitude certainly warrants visual monitoring. So what I would say in summary is that visual observation of variable stars remains scientifically important, much valued. To take it to an extreme, you might get a medal like Albert Jones did. And anybody on this this webinar can make a contribution to science by starting to undertake visual photometry, or continuing to undertake visual photometry and submitting the data to the AAVSO. So that concludes the presentation, and I say thank you for you all attending. Over to you, Lauren.
Thank you very much, Mr. Toone. That was excellent, and I'd like to second your concluding point there, that there's still a lot of science that can be done by visual observers, and every observation counts. Now, we're going to go to the Q&A. However, I had a thought that real quick before we start the Q&A, I would like to show for all of the observers who will soon be wanting to make their own observations. We have here on the AAVSO website, if you just go to the main page and you scroll down, then right here, front and center, pick a star. You can type in the name of a star and then hit create a finder chart. That will take you to our VSP chart tool, and you'll be able to use that chart to make your own estimates. Now, in this case, you'd want to configure it by hitting plot another chart, because Betelgeuse is a naked eye variable. That's a telescope chart by default, but definitely check out VSP. And we also have a visual observing manual at aavso.org/visual-star-observing-manual. All right, now let's go ahead and go to the Q&A. So let's start out with a couple of general questions and then go to red stars, because I noticed we have quite a lot of questions about that. So first, a general question. This was addressed at the beginning of your talk, Mr. Toone, when you had said that at this point, most photometry is being done with CCD cameras. Maruf Mian had asked, when you say that, does that include CMOS cameras under that umbrella? You're still muted.
What type of camera?
CMOS cameras. Maruf was asking if that was included when you were talking about how most people use CCD cameras to do photometry. At the very beginning of your talk, you had said that. So he had asked, is CMOS included under that umbrella?
I'm not aware of what CMOS is.
Okay. So I'm going to answer that question then, which is that yes, CMOS is starting to become used in place of CCD cameras, and I believe that it would be included because the CMOS data points which are produced are transformed to Johnson V just like CCD are. So Maruf, I would say that the answer to that is yes. All right, And next, Kevin Haslog had asked, do you have any advice for observers who live in urban environments?
Yes, try to find a dark area if you possibly can. Urban environments is quite a challenge, but take some inspiration from Gary Poyner, who I've just introduced to you. He lives in the second largest city in the UK, heavily light polluted, but he produces thousands and thousands of observations. And what you need to do is just to try to shield wherever you observe from the direct light, and use aperture if you can. If that will look at a small field of view. If you've got an observatory as well, that would also help, because that will shield you a lot from the direct light on the sky glow. So that would be helpful. But somehow you've got to get out of the direct light from the lighting, which is prevalent in urban areas.
That's good advice. Thank you. Now, next up, we've got a question from Neil Simmons about clouds. You'd mentioned observing on partly cloudy nights. Neil says that he knows some people who stop observing at the first sighting of the smallest cloud, and others that will keep observing for as long as the part of the sky they're observing looks clear-ish. What would you say is a good time to say stop?
Yes, if the photometric conditions are poor, and you've got constant haze or patchy haze, that's a real problem. But if the sky is only partly clear and the transparency is relatively good, and particularly if you don't have moonlight as well, then there's no reason why you can't continue observing. In fact, what I find where I'm observing from, I only get 10% of the nights clear. And 30%, however, are partly clear. So the bulk of my observing is undertaken in partially clear conditions. And so if I just waited for the 10% of the nights which are clear, then I wouldn't get most of my data. And I think that applies for lots of other observers around the world. So whilst the sky is clear, or partly clear, it's worthwhile observing. If it's fast-moving cloud and you don't have time to make a reasonably steady observation, then no, maybe stop at that point. But if it's partly clear and you've got time to make that light estimate, go ahead, do it.
Okay, thank you. That was one I was curious about too. Let's move to some of the questions about red stars. Namely, we've had a couple different people ask about the technique of defocusing. Have you used that technique? What do you think of it? Would you recommend it?
Yes, you can. I didn't mention it in the presentation. The best approach with red stars, it's difficult to compare a red with a white star, and you could see that on the example I gave. Actually, it's slightly the variable was slightly orange compared to the comparison stars, which were white. And that contrast is a bit of a challenge. So the way to tackle this, I mentioned that you use the smallest aperture to render both the comparison stars and the variable visible. So it reduces the color effect. But also, if that's not possible, simply because of the aperture you're using, the instruments, and the color is intense, then yes, do also the defocusing, because then you're comparing disks of light rather than point sources, and that is and I use it. I do that. If I have any uncertainty about making the estimate, then because it's marginal, then yes, do the defocusing. It's a good technique.
Thank you. All right, so next up, John Merle had asked, what impact does color blindness have on observations? John says that he knows one person who is not a variable star observer, but is unable to see red laser pointers. So in the example of someone who's colorblind like that, what does that affect?
Well, it will affect your data. It will give you an offset from whatever sequence you're using and the color of the sequence, because it's your perception of the color of the variable compared with the color of the sequence, and that will create the offset between you and V data and perhaps other observers as well. So I can't say what individual observers with color blindness. It depends what they're blind to, but there will be an offset. The important thing is don't worry about it. Do the observations. And you can plot your data so long as you're seeing the variation, the same type of variation that other observers are recording. It doesn't matter. Your own data set is the important thing. And yes, you'll have an offset. Can't work out what that offset is. But the important thing is you record that data, submit it to the database, and you can filter your data, produce your own light curve. It doesn't matter that you're colorblind and that you're offset and systematically different from everybody else. It doesn't matter.
Thank you. That's a good point about the offset being systematic. So speaking of those types of offsets, Michael Poxon had submitted a comment just now about defocusing red stars. Michael had said, make sure that you use that technique consistently or you get weird results when transitioning from defocus to focus. Do you have any comments on that?
Yeah, Michael's right. Yeah, I know Michael, and he's an experienced observer. And yes, you should show consistency in your approach. And you do see offsets. It's like moving from one instrument to another. And so you're estimating at a brighter intensity level. That also introduces an offset. You have to be aware of that. But the important thing is always record exactly what you see. And then write that down. And if there are systematic differences introduced because of this, or because you're changing instruments, then you'll recognize that in time for each variable. So the important thing is try to be consistent in your observing technique in order to reduce these effects.
Okay, thank you. All right, let's see, next question. So have you ever observed the apparent brightness of a red variable changing the longer you spend on the field, even if you're using the short glances technique? Like the more times you glance at it, the more your estimate changes. Have you ever noticed that?
Oh, yeah, well, there's no real true color change that I have seen in making an observation, but it can appear that way if you do take long stares at a particular red variable. So this is why you need to do the quick glance method and to negate that effect, because it will make you think that it will create uncertainty in the estimate, and so no, try not to get to that point by making the quick glance approach, or actually stopping the aperture down on the telescope or using a smaller instrument, as I advised earlier, to reduce that effect, and defocus, just so that and do the estimate pretty quick. The eyes should be able to work out the relative brightness of the object and do that comparison within a couple of seconds.
Interesting, thank you. I just asked because when I first started observing red variables, I figured, like photometry, the longer your baseline and the more you kind of average the estimates, the more accurate it would get. But I found the exact opposite. So,
well, on that point, what you can do if you feel a little uncertainty about your estimate, what I suggest you do is record the observation, move on to other objects, run through your stars and then return to this star and make another observation. And if there's a difference, then maybe do another one a little bit later on and see if that settles. It may be that the first time for fatigue or other reasons, it was not an accurate estimate. So suggest you return and repeat the observation at a later date, rather than keep straining to make that observation work, because then you're going to get all kinds of external effects which might bias the observation.
Interesting. Okay, thank you. Okay, so next question comes from Jeremy Shears, who had asked, what is your observing strategy? West to east, favorite stars first? What time of night do you prefer?
Hello, Jeremy. I thought I'd already told you this in person, but my technique is, as soon as I go outside, I start in the west, because the stars are they're the first ones that will disappear. I'll do a quick run through binocular stars in the west, then I'll run through a number of telescopic stars in the west, and then I'll alternately move across the sky towards the east, until the whole sky is covered on the observing program. Then, of course, if it's winter, then I'll repeat that process in the morning sky until twilight sets in, and so that way cover the full sky in one night. In terms of the type of stars which I follow, there's two distinct groups: eruptive stars and red stars. The red stars only need observing 3 times a month. So what I try to do is to target those on the 5th and the 15th and the 25th of the month, so that I get them equally spaced 10 days apart. Doesn't always work that way because of the weather, but that's the technique for red stars. Whereas for eruptive stars, or Colbor stars, for instance, they merit observing every night. And so I will simply observe those whenever it's clear.
All right, thank you. And Jeremy Shears had one more question here, which was, do you write down each estimate?
Yes, I do. And that goes into the logbook, which I showed in the presentation.
Thank you.
And I can do that in 1 minute. So that means the estimate itself takes only a few seconds.
Okay, let's see. Next question comes from Pradeep Karamakar, who had asked, for visual photometry, what equipment would you suggest for a first-time observer?
Binoculars. Binoculars are great instruments for a starter. I started out with binoculars, and there were many years where I was just observing binocular variables, because there's so many, and it's easy to do. Binoculars are cheap. You've probably already got a pair of binoculars, and you're using 2 eyes rather than 1, and so it's so comfortable to make that first estimate. So please use binoculars, and all you need is some advice on which stars to start with, and you'll very soon have success with binoculars, with some good stars like Z Ursa Majoris or Scuti. These vary. If you monitor it over a few months, you'll get variation, and some of the brighter Mira variable stars. Take Mira itself at the moment; it's magnitude 2, very bright, and over the next few months it will fade, and you can follow that in binoculars. That would be a good target.
For sure. All right, thanks. Let's see. So next question comes from Joyce Guzik, who had asked, are there issues with wearing prescription glasses to be aware of?
No, not at all. You just take the glasses off. I would take these off and look through the telescope, use the binoculars. The binoculars and the telescope will adjust everything. You don't need the glasses. Take them away. Take away contact lenses. You just need your eye and the instrument to undertake the observation.
Thank you. All right, and our next couple questions come from Sergey Hoste, who had asked some interesting ones. I haven't actually heard of either of these things before. He asked if you have any advice on using photometric aids such as artificial comparison stars.
No. I would suggest that you use the sequences, comparison stars on the sequences from the official charts of the BAA VSS. They're chosen for a reason. We want everybody's data to be used and aligned with those sequences. I would suggest use conventional comparison stars used on official charts. I think that's quite important.
Yeah, I would agree that that's quite important. You're definitely, and it helps to have a star placed effectively at infinity on the other side of the same atmosphere that you're looking at your target through, I would say. So,
No.
Yeah. And then the next question from Sergey was, if you know anything about using small doses of retinol to increase eye sensitivity?
No. And why do that? If you need to see a fainter star, use a higher magnification or rely on the instrument which you're using. No, let's not leave the eyes alone. Let the eye do the job with the optical aid, which is your binocular or telescope.
I second that. All right. Next question comes from D. Sharpless, who had asked, does the AVSO have a list of binocular variables? And that's one that I can answer, which is that yes, we do. And I will put the link for that into the chat so that anyone can access it. It's just aavso.org/aavso-binocular-program. So have fun with it.
And if you do work on those program stars, that helps, because there's lots of other people looking at the same stars, and then if you can get more and more data on those stars, the more scientifically useful it is. So and those stars are chosen for a particular reason, because they're suitable for visual photometry.
Yes, absolutely. Those are usually the most scientifically interesting of the bright stars. So that's a good list to work from. Okay. Next question. Do you ever make estimates with the naked eye?
Yes. And in keeping with the advice to use the smallest aperture for rendering the comparison star and variable visible, in some cases, yes, I have to go to naked eye. If we take Mu Cephei, the Garnet star, you take Myra, the other morning I was observing that with the naked eye, even though it was relatively low down. Yes, that's more. You use whatever's right for making the observation, and yes, sometimes you have to go with the naked eye. Naked eye is good. Doesn't cost you anything to. You've got your eyes. You can use it, and that's the time to use optical aid. So you can wear your glasses. If you're short-sighted and you want to see something maybe a fifth magnitude, it's better off using your naked eye and glasses rather than using small magnification binoculars. So the answer is yes.
Right, thank you. Okay, have you ever witnessed a flare at the eyepiece?
Yeah. Flare. I've seen flickering.
Flickering. Okay.
I've seen variable stars flicker, It's an astounding sight. Sometimes the first thing is you think, well, is it real? The check that you do is that you look carefully at the comparison stars. If they're still steady, and then you move back to the variable star and it's still flickering away, you know it's real. And I've seen it in quite a few CVs. I've seen it in an AGN, I've seen it in U Geminorum. I've seen it several times in Oryx Andromeda. That's the more recent event. So it's real. It happens, and it can be picked up by visual observers, and it's a tremendous sight when you see it.
Wow, yeah, that sounds amazing. I hope I get to see something like that someday. I see that Michael Poxon added a comment just now that he once saw CQ Tauri fade by 0.9 magnitudes in 20 seconds. That's incredible.
Yeah,
So
I think the most I've seen is just over half a magnitude, but it's certainly real, and you can see that by checking out the comparison stars.
awesome. So you're talking about when you're talking about this flickering behavior on short time scales of like a second, less than a second, or tens of seconds.
Well, you can see it changing in seconds.
Wow.
What I've seen with RxAnd is slightly periodic as well. I think Gary Poynter has found the same, because I remember putting out an alert once when it was happening, and Gary took a look at it, and he did a series of visual observations, and he produced a light curve of the flickering. I've seen it, the object dim. In the case of RxAnd, I saw it dim. It was more than a magnitude, and it came back, and the period was in the order of about 45 seconds, but it didn't last for long, and it faded away. The flickering reduced, and the star became steady after about 5 minutes. So this doesn't happen very long, but it's worthwhile catching. You're very lucky if you catch it. But the more you observe these objects, the more you're going to, that's going to increase your chances of picking up flickering.
Wow, that's fascinating. Okay, so on the topic of very short period variations, although not that short, do you have a favorite couple of very short period pulsators that you could track changing in a single night, for example?
Yes, although I haven't focused on this for many, many years. Dwarf Cepheids are a good target, and if you take SX Phoenicis, it's a southern variable, but it can be observed from northern tropical areas. And I've observed it from the Canary Islands. I think it's 28 degrees north. And I produced a light curve in one night, covering 4 maxima and 4 minima.
Wow.
The variation is only about 0.7 or 0.8 of a magnitude, but visually, yes, you can pick it up. And I've got a light curve. I think I've published it a few places, so it is a good target. So I would recommend going for that if you can pick it up from your latitude.
All right, thank you. I see another comment here from Michael Poxon, who said that CY Aquarii is another one with a period of 90 minutes.
Yes, yes. CY is 90 minutes, and SX Phoenicis, I think, is 79 minutes. So it's slightly shorter, so you can probably get more cycles in the night.
All right, thank you. All right, here's a question from Sergey Hoste, who had asked, hypothetically, what would be the correct procedure for submitting an alert based on a visual observation?
Right, I work within the BAA. We have an alert system, and so there is a procedure for that, and so you need to subscribe to it, and then you can post the alerts. I believe BAA VSS have the same.
Yes, we do have a alerts system. I'm not sure what the procedure is for submitting an alert based on a visual observation. I do know that when you're submitting your observations in WebOps, there is a box that you can tick that says unusual activity. I've never had cause to tick it, so I don't know what happens after you press that,
Yeah.
but probably something to do with the
Yeah, I
alert
think
system.
VSNet have an alert system also. So
Ah,
and
yes.
so there are a few alerts to put out any unusual behaviour, and it's important to do so because if there is really dramatic, and I did it for AGPEG, and that allows everybody else to start working on this unusual behaviour, including professional astronomers who might want targeted opportunities for satellites.
Yes, for sure. Okay. Let's see, a couple more questions. So do you have any suggestions for someone who's just starting to try and draw up a visual program of stars they're going to monitor? What types of variables should they be looking at?
I would say binocular, similar to an earlier question, binocular variables is always a good start. Target some Mira variables, which come very bright, Chi Cygnus, Mira, and there's a few others, TCVI, which comes bright. It's circumpolar for Northern Hemisphere. There's for the Southern Hemisphere, or Carine, is very bright, often naked eye Mira variable. So target those. Also, some bright semi-regular stars. Or Doradus for the Southern Hemisphere is one. L2 Puppis is another for the Southern Hemisphere. Northern Hemisphere, binoculars to go for Zedus Majoris. That's inside the bowl of the plow. So that's easy to pick up. And if you observe it for 4 months, you'll get a light curve. It's guaranteed. And all you need is binoculars. So there's a number of stars which I'd recommend, including those just now.
Excellent, thank you. Okay, and one more question here is, when you showed your light curve of AB Auriga, and it had that eclipse in it, how long was that eclipse?
It wasn't an eclipse. What I and the jury's out what it was. It looks like an eclipse, doesn't it? It's very dramatic. The best interpretation of that, this is a Herbig star, and it's got a lot of dust on a surrounding that star. We think it's a planetary system which is evolving. It's a very young star. And there's clumps of material forming. There's a lot of Hubble. If you Google AB Auriga, you'll get some very good, interesting Hubble Space Telescope images of that dust cloud and planet, and lots of information on planet forming clumps of data. Now, what I think I saw on that occasion was a change in medium. It's moving from a less dense part of the cloud into a more dense area, and this was the leading edge for it. And so it suddenly hit that leading edge, and it faded away. And then you're left into a much more volatile region. I've only seen 2 fades in AB Auriga. There was one in 2019, which was not quite so deep. I think that was just a lump of material. But in this case, there is a difference because afterwards, the object was much fainter. There was a lot of variation, including flickering. And subsequent to this event, which occurred in 1997, AB Auriga has steadily faded. It's faded from a mean of 6.8 to 7.3. And you see that in the long-term light curve. It's a fascinating star.
Yeah, absolutely. Sounds it. So we have one relevant comment here from Michael Poxon, who had said the case of that dimming in AB Auriga was probably obscuration by a forming planetesimal, and that AB is in a large star forming region, as I think you mentioned, with lots of young stellar objects nearby.
Yeah,
So,
my interpretation of that is that the second fade in 2019 is what Michael has just described. It could well be a planetoid because it was just a straightforward fade, and then the light level before and after was the same. Whereas the light curve, which I demonstrated during the presentation, there was a big difference between before and after, and that wouldn't be due to a planetoid.
right, okay. All right, thank you. So it looks like that's it for the questions. We do have a couple of comments here, which I'll read out. And while I'm doing that, if anyone has any last minute questions they want to sneak in, please do so. One is from Michael Rapp. Hi, Michael. Glad to see you here. He said that your discussion of position angle has just instantly improved his visual estimates from now on. And thank you for
Good
that.
to hear. I think if you're already an experienced observer or semi-experienced, if there's one takeaway from the advice given here today, it is about position angle, and it's often unrecognized. And so I'm very pleased if that has helped just a single observer.
I think it's helped quite a lot more than just a single observer today. That's something that I had not heard about either, but now I'm going to be applying it in my observing. So thank you.
That's good.
Another comment here from Francesc Clepez. I apologize if I mispronounced your name. He said that he would like to share that Myra is at second magnitude, like you mentioned, and it's a real pleasure to be able to see a variable star with the naked eye. So I second that.
Sure is, and the first ones discovered were before the telescopic era, with the supernova which was seen in ancient times, but also Myra itself in 1596. So the telescope didn't come along until some 10, 15 years later. So naked eye is just as good as any other form of photometry. It's similar to binocular because you're using two eyes for binoculars, and that is certainly an advantage.
All right. And then the last question we have here is from Pradeep Karmakar, who had asked if you would mind sharing your email address.
Yes, it's readily available, and yes, Lauren, if you want to share it, that's fine. It's on display on the BAA webpage, and so I am contactable, readily contactable.
Okay.
I always like to hear from other observers. It's great when with the likes of Gary Poynard, Rod Stubbings, all the great observers, we're all in contact by email. And we share our experiences, and more people undertaking visual photometry, sharing experiences is good.
That's great. Do you mind if I paste your email address into the chat so that if someone wants to contact you, they can copy paste from there?
Certainly, no problem.
Okay, I'm going to do that then. There you go. Okay, and it looks like that is now it for the questions. So I'm going to go ahead and put up the end card here and give a couple of closing announcements. Okay, so first of all, the most important announcement of all, I would like to extend a huge heartfelt thank you to you, Mr. Toone, for sharing your time and knowledge with us today. I would also like to thank again our sponsors, DC3 Dreams and Boyce Astro. DC3 Dreams provides high-end observatory automation and web-based multi-user remote imaging. The BAA VSS net observatories use DC3 Dreams ACP Expert for the Bright Star monitors and other programs. The AAVSO Photometrical Sky Survey Project, also known as APAS, has used ACP Expert's AI scheduler to automatically acquire over 500,000 star fields, hands-off, at a rate of 1,000 square degrees per night. This has resulted in photometry for over 128 million objects in about 99% of the sky. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. All right, now some good news for all of you. Today's webinar has been recorded, and the recording will soon be made available for free on the AAVSO's YouTube channel, where you can find a full library of webinars just like these. Go check it out, and while you're there, please consider subscribing to our channel. Not only will you be notified each time a new educational video is posted, but by hitting that little subscribe button, you will be making YouTube more likely to suggest our videos to others and helping us increase our educational reach. That's just one more way that you can help support the AAVSO. Speaking of support, this webinar series is being supported by you, the viewer. So please, if you're not a member, join the AAVSO. AAVSO membership comes with a very wide array of benefits, including free access to our mentorship program, where you can continue your learning by pairing up with an advanced visual observer. And as always, we would be so grateful if you would consider donating to the AAVSO. Every donation matters and goes towards making programs like this one come to life.